So partition function is the problem that when we work with energy-based models as explicit probabilistic model, we have to deal either to compute the likelihood or its gradient with this intractable sum. So I'll talk about score matching, say a few words about sort of contrastive methods. No, I won't spend much time on this one. And I already talked about autoencoders. I'll say a few more words about them as well. And then we'll talk about sampling issues and some of the fundamental difficulties in trying to sample from probabilistic models. And then I'll have a quick summary of a tutorial I gave at ACL, the Association for Computational Linguistics, that was held last week. So that's about the application of deep learning to NLP. I'll go very quickly through the slide. I encourage you to look at the slides themselves. There's also a video of the tutorial that was given last week. You can look at the video if you want to catch more detail and hear Chris Manning and Richard Solcher talk about the same subject. So score matching. The idea is, instead of trying to match the density, we're going to match the first derivative of the density. So that means the derivative of the density with respect to the input. Now, the good thing about this is if there is an energy model, in other words, P of x is e to the something normalized, when you compute the derivative with respect to x, the partition function, the normalization constant goes away. It doesn't depend on x. Right, so then if you're just trying to match the first derivative, there's no partition function to deal with explicitly. Now, the problem is, so here's let's say P is your model, and Q is the unknown generating distribution. So what score matching tries to do is something like this. Say, well, let's make the distance between our estimated score, the first derivative of our model, as close as possible to the true score. Now, unfortunately, we don't know, of course, the true density. We only have samples, but it turns out that you can expand that, integral into this that has here a constant that doesn't depend on parameters, and here things you can compute and over which you can write this expectation over the true density, but that expectation can be replaced by an empirical mean over the training data, and so you can actually minimize this thing. So this is just the norm of the score from your model, and this is the sum of the diagonal second derivatives. So that's what score matching is about. Different algorithms in which you define an energy function and then you minimize that criterion. And for reference to some of the things I talked about on Tuesday, like the contractive autoencoder, it turns out that the first term here, this the square of the score, is essentially squared reconstruction error. If you remember, at least for some models like the Gaussian RBM. If you remember, I said that the denoising autoencoder was estimating the score in the difference between reconstruction and input. So if you take reconstruction minus input and you square it, it's just reconstruction error. In other words, this thing is just reconstruction error. What about that thing? Well, it turns out in the case of the Gaussian RBM, it's this. So HI is the output of sigmoidal heating unit. And this happens to be almost the same as the contractive penalty we use for contractive autoencoders. So all of these different methods are very strangely very close to each other. All right, and to make the connection even more direct here, I'm considering denoising autoencoders. So in denoising autoencoders, remind you that what we're doing is we're putting in a clean input. We are perturbating it. This is x tilde. So we get a corrupted input. We throw it into our autoencoder. We get a reconstruction. And then we minimize the difference between that reconstruction and the clean input. So that's denoising, right? We take a noisy input and we try to map it to a clean input. So that's the denoising autoencoder training criterion. It turns out you can write it like this. Let me decompose that in more detail. So we have two vectors here that we're looking at. And you can think about it geometrically. So the data is concentrating near some manifold. Let's say you have a clean input here near the manifold, you corrupt it, you go orthogonal to the manifold, you get an x tilde. Now the difference between these two vectors, x minus x tilde, is what nature tells us about where the density is concentrating. It's what nature tells us about the score, right? It's because if you think about it, if you start from x tilde and you go in the direction of x, you're going towards a direction of higher probability. And that's just what nature tells us, right? So you take, it just comes out of the fact that we're working with these high dimensional spaces in which the data is concentrated in low dimensional structures. And just by virtue of that, you'll have that the difference here is a very strong indicator of the direction of the score. Starting at x tilde, this vector is a score at x tilde. Okay, so that's what nature tells us, and what the model estimates as a score, we've sort of declared to be the reconstruction minus the input. And so if you make this minus this as small as possible, so you just subtract these two things from each other, you get the denoising reconstruction error. And so that's one way to justify, sort of hand-waving way of justifying that the denoising autoencoder is estimating scores. You can make that more formal. In the work that was done by Pascal Vincent, who's here, he did it for a variant of the Gaussian RBM, but in a more recent paper I showed that every autoencoder that minimizes reconstruction error, squared error reconstruction, is doing score matching and is also doing more than that, but that's sort of a very generic property of denoising and also contractive autoencoders. Okay, I'm going to skip the details of that actually. There's another training criterion or variant of that has been used in several papers that avoids the partition function problem, which, for example, is used by the Google gang that have built the Google image search. And so this E here is the energy function again. X is your observed example, and x tilde is going to be a corrupted example. So same kind of story. So the actors are similar as in the denoising autoencoder. And so we're going to sample our training examples, which we call positive examples. We're going to sample negative examples using some kind of corruption process. And what we're going to do is minimize this criterion. So what is this criterion saying? It says if the energy of the observed example is at least one smaller than the energy of the negative example, which is supposed to be bad, is supposed to be high, then the gradient is 0 and the cost is 0. But if the difference is less than 1, then please pull this down. In other words, make the energy of the true observed example lower and make the energy of this negative example higher. All right, it's a very simple thing, and it works. Now, let me just switch gear to something related to the partition function and sampling from probabilistic models and inference. There is a really sad fact, which you come to realize when you start playing with RBMs and Boltzmann machines and many other probabilistic models. Which is that as training progresses, it becomes harder to train because your density becomes more concentrated. So let me decompose that statement. First of all, it's true of almost any learning algorithm that does some kind of density estimation, that you start during training by a model that kind of puts probability mass everywhere. Okay? So let's say you get your default model. And then as you get examples and you optimize your likelihood or something, a proxy for the likelihood, you start putting more your model starts putting more probability mass where the examples are or around the examples. And it concentrates and concentrates and concentrates. And so what happens is initially when your model still has a pretty smooth density, the modes of the distribution represented by your model are not separated too much by empty void. In fact, there are regions between the modes that allow you to go from one mode to the other mode, staying in a reasonably high density place. So why is that important? Because all mixing algorithms, all MCMC methods proceed by making small changes such that the next move brings you to a high probability configuration. You never go to a low probability configuration. I mean, you go there, but with equally low probability. That's the idea of MCMC. You move to a place that's supposed to be likely. And so if there are zones in between modes that have very small density, then the chances of actually crossing this big C in the middle is very small. And in high dimensional spaces, it becomes exponentially small. And that's a huge problem, because if you rely on the MCMC to give you the gradient, as we do in Boltzmann machines, then there's a chicken and egg problem, right? Initially, we get nice gradients because our MCMC is able to visit all the modes. And so our estimator of the gradient is very reliable and sort of converges quickly. Whereas after some point during training, the modes get more separated, and you start a chain here, it will hop around here, but it will never cross this. So that's the problem of mixing, and the difficulty here is that because we use sampling in the inner loop of training, we're kind of stuck. So here's maybe something that could help us. Depth. Turns out, at least according to my intuition and according to some experiments we run, that if you have deeper models, mixing become much easier. And the intuition why this happens comes from the hypothesis that deeper representations allow you to better disentangle the underlying factors of variation. Of course, as I said at the beginning of my lectures, this is what we would like. But if it did happen, at least to some degree, it would make sampling much easier. I'm going to explain why. Let me give an example that's kind of easier. Imagine that you had a model that was disentangling the factors of variation. So let's say your data are images, and it figures out that one of the factors maybe is sort of a lighting, like a reverse video bit. So if it's on, then when it flips from 0 to 1, it reverses foreground and background illumination. And maybe you have other bits that say what is the class of the object in the input, and you have other bits that tell about geometry and so on. So of course this is an ideal world, but just to give you an intuition of why this would make life much easier. So instead of sampling in pixel space, let's say we were sampling in this representation space that's more abstract. Well, what would happen is now you can make small changes in that space, like flipping the reverse video bit, and move from one mode to a completely different mode in input space. But semantically speaking, these are actually pretty similar. Similarly, you could flip from one category to another category by just changing one bit in your representation space, whereas you couldn't do that in pixel space. You would need to change a lot of bits to go from, say, a 9 to a 3. And we did experiments where we actually see that happening. Of course, we don't have a video bit and class bits, but we have things that are abstract enough that suddenly mixing becomes much easier. So in those pictures, what I'm showing is an interpolation between two samples. Here, say a 9 and a 3, so these are real examples. And we're doing sort of a linear interpolation to get a mental picture of what things look like in the space that we're visualizing, the different representations. So this is just, the first line is in pixel space. And you can see if you linearly interpolate between a 3 and a 9, you have things in the middle that just like, the addition of a 3 and a 9. It's kind of a hybrid strange thing, which should have low probability, by the way, according to our models. And that's why if you try to do, Gibbs sampling or MCMC in that space, it just doesn't work. Or it's more difficult, rather. I mean, these examples are not that difficult, but it's easy to understand what is going on. Now, what happens here is we're doing the same thing, but in the representation of the first layer and second layer, either of a deep belief net or a stack of contractive autoencoders. And what you might see here, for example, at the top layer, is that we almost suddenly jump from a 9 to a 3. Of course, there are a few pixels difference, but we never go through these intermediate stages of sort of mixed up low density examples. And so mixing in that space is way easier. What we also see in this example is that the higher level representations have kind of unfolded the manifolds. Remember, I've tried to tell you about this idea that densities concentrate in some regions, and these manifolds are really highly curved, and that's what makes the learning problem difficult. But when you move to these higher level representations, it's like if those manifolds were flattened. And one way to picture that this is happening is, so if you have a curvy manifold, and you look at the linear interpolation between 2 points, if those 2 points are very close to each other, then you'll stay on the manifold. If those 2 points are a bit farther from each other, because of the curvature of the manifold, you have to go through these empty spaces in between, right? So what this is saying is that the manifolds are much flatter, meaning that when you linearly interpolate, you get nice things, which you don't if the manifold is highly curved. We did other experiments to validate that idea using either DBNs or the stacked contractive autoencoders, where in both cases we sample from the top level using an MCMC, and then after a while we generate, well, actually at any point we can see what's in the mind of the model by projecting that back in pixel space and then visualizing these examples. And what we did in these experiments is we take the generated examples in our chain, and we try to find what is their category using a simple classifier, like here I think was a nearest neighbor classifier. So it's not biased towards a particular model. And then we just count in our chain how many different classes we have visited over a particular run. And then we do a histogram of how many classes we have visited. And that's a way to see how fast is the model mixing from mode to mode. We don't know what real modes are, but we know that the digits in MNIST should be modes, right? And so we can just use that as a proxy for seeing at which speed the sampling algorithm is visiting different modes. And what we see here is that the difference between a 1 and 2 layer models, the DBN and the contractive autoencoders, and basically what you see is the histogram of number of classes visited shifting to the right as you go higher up in the representation space. So that's really cool. I call that an MCMC miracle. There's another miracle that comes with these algorithms, which is that there's actually another problem with MCMC, which is called Burnin. So it's the time it takes for your chains to go from some random configuration to one that is with high probability. And that can take a while. This is, how much time should you wait before you consider your MCMC samples to be valid samples from your distribution? And for example, when you do contrasted divergence with k steps, k is supposed to represent, how long you're willing to wait because of the burn-in. It turns out that when you train models as autoencoders or as denoising autoencoders, you're actually training them to do super fast burn-in, because you take a noisy corrupted example and you train the model to map that into a clean example. So to go from noisy examples to high probability examples. And so the burn-in is almost instantaneous. There's, okay, I'm gonna skip the other stories here because time is flying. So I guess I'm asking the question, well, do we actually need an explicit probabilistic model? I mean, if we have these autoencoders, maybe we can get away with no partition function, no negative feedback loop between sampling and learning, which I was talking about. Inference, we still have to deal with that somehow, and not much work has been done yet. Could be done by adding sort of lateral recurrent connections in a way that's similar to what is done in sparse coding, for example. Okay, there are a lot of open questions. Here are a few. Some I have raised already in my presentation. The most important open question is, what is a good representation? How do we characterize a good representation? So I've talked about this very vague idea of disentangling the underlying factors. It's vague because we don't know what they truly are, so how do we put that into sort of training criteria or architecture? There is something I didn't talk much about, which is when we're doing inference, so in other words, we're given an input and trying to figure out what are the underlying causes, like finding a posterior or a representation. Very very often we end up making very strong assumptions, like that this is supposed to be unimodal or have a few modes. What if in reality, in the world around us, we need to handle much more complicated models? Maybe we can get away with having explicit latent variables, avoiding that. Let's see, yeah, that's basically what this is saying. Basically, instead, directly learn to produce good representation instead of going through the intermediate step of some kind of samples or approximation of the posterior. One question I think I've answered is, should learned representations be low dimensional or sparse, saturated, and high dimensional? And the answer is they should be sparse, saturated, high dimensional. I mean, yeah, it's obvious. Well, 12 years ago I thought it was the other way around, and I did so-called nonlinear dimensionality reduction, and then I found it didn't work, and there were good reasons for that, and now I understand better why. And I guess one of the really hard questions which we have to tackle is that as soon as you try training really deeper architectures, and it's most obvious in things like recurrent nets or recursive nets, the optimization problem becomes fundamentally hard. I mean, I've talked about these local minima, and we really have to do a lot more work to understand these local minima and the structure of the dynamics of learning, and then maybe use that to design better optimization/learning algorithms. So this is a really hard problem, and it has immediate impact in applications. So people like Google, researchers like those at Google are trying to train huge networks on huge quantities of data, and their number one problems is underfitting. And that means it's really, they don't know how to get the training error down because the optimization problem is fundamentally difficult. Okay, so now I'm gonna do like a 15, 20-minute summary of a 2.5 hours tutorial, but you can look at the video, as I said, and some of the slides, of course, I've stolen and put here. I'll just give you some highlights, right? So one of the main thing is that there are already really impressive results from deep learning in NLP. It's one of the areas of application which is already beating the state of the art in many cases, and people in industry like IBM, Google, Microsoft are taking these models and putting them into their systems. So for example, I'm citing some work from Mikolov and collaborators on language models which are used in speech recognition, and they're getting improvements that are amazing for that world. So these kinds of improvements in the world of speech recognition, like 2 points improvement, 2 or 3 points improvement, are unheard of. I mean, they typically fight for 0.1% improvement, and suddenly these guys come and make 2-3 points improvement. It's they're amazed. And these guys, for example, these are Toronto guys, these are Microsoft guys. They have put these kinds, so these are on the acoustic side, these are on the language side, both doing speech recognition. And again, they have really substantial improvements on the various systems they're building. As I said, I think on Monday, there was a New York Times article talking about some of these results. No, that's not. That was about the Andrew Ng thing. No, I think they also mentioned this. Anyways, you can read about it, and just sort of to impress on you the sort of breadth of applications of these types of models already in NLP. Here's a list of the applications that are already out there. So language modeling is predicting the joint probability of sequences of words, and it's applied in speech recognition and machine translation and text compression, I forgot to mention. Acoustic modeling is predicting the phonemes given the acoustic. Part of speech tagging is predicting, well, is this a verb or a subject or something like, a verb or a noun or something like that. Chunking is sort of breaking the sentence into pieces. Named entity recognition is identifying words that refer to particular entities in the world, like proper nouns, like names of people. There are many ways you could write down the name of a person or the name of a place, and you want to identify which it is. Semantic role labeling is a kind of parsing, actually, that says which part of the sentence is doing what role, say for the word, for the verb. Is this the action? Is this the object on which the verb is applied, and things like that. And then there's a traditional parsing, sentiment analysis, trying to take a sentence and say, is this positive or negative? And it's very useful for commercial purposes, analyzing internet behavior. Paraphrasing is taking two sentences and saying, is one essentially saying the same thing as the other, and just rephrased in a different way. And it's obviously useful, for example, in search engines. Question answering is answering questions. In other words, filling in, you can think of as filling in partially given answers, partially given sentences. Word sense ambiguation is about saying which of the senses of a word is the one that semantically makes sense. So one of the models that sort of started, I think, the effort in deep learning and NLP is this thing I did in the late 90s that was published at NIPS 2000, and then a few years later as a journal paper, called the Neural Probabilistic Language Model. It was a very simple thing, but it's still sort of the basis of many of the models that are used in this area. So you take your sequence of words, and so these words are symbols. You can think of them as integers or one-hot codes, where there's a 1 at the position corresponding to the word and zeros at other positions. And you map these symbols into fixed size vectors, and you map them with a matrix that has one row or one column for each of the words. And you can think of that just as if you encode them as one-hot vectors, as a kind of convolutional network, actually, which uses the same weights at all the word positions. So these are shared parameters across words, doesn't depend on the word position. Now you concatenate these vectors, and then you have a regular MLP, well, with sort of the little detail that it has a huge number of outputs, because it has one output for each possible word in your vocabulary, which could be tens of thousands, hundreds of thousands, or even a million or more. And so that's the model. The motivation for this is that to maximize likelihood, what's going on is that the model learns to map words that have that can be replaced by another word and come into sort of similar contexts, to map sort of replaceable words by very nearby points in this space of these vectors. And you can visualize, let me just blah, blah, blah. You can visualize these things by projecting using nonlinear dimensional reduction. Nonlinear dimensional reduction is actually useful for visualization. That's what you should be using for. I mean, we want 2D things that we can look at. So you can sort of map the words in 2D and then zoom in, and you see things like, you know, countries coming here, and things having to do with the European Union here, and parliaments and elections here, and whatever, all kinds of verbs here, and so on. So these things, as I said, work great. They learn these word embeddings. I'm going to skip. And they can be trained in various ways. One of the sort of important pieces of work in this area is the work done by Ronak Oliver and Jason Weston, starting in 2008. Then they had a longer list of authors in the journal paper last year. And among other things, they applied these kinds of models to a number of NLP tasks. They've shown that they could essentially reach the state of the art with these tasks. They use unsupervised pre-training by training a model on huge quantities of unlabeled text and then initialize their supervised models for each of the tasks using these embeddings. It is also shown that if you do supervised fine-tuning, you get improvements. And we skip. So one of the fundamental problems with these kinds of models is what I call the output bottleneck, that a lot of the computation ends up being done to predict the next word, because you have this output layer which maybe has hundreds or thousands of hidden units, and then you have your hidden layer that has hundreds or thousands of hidden units, and then you have your output layer that has tens or hundreds of thousands of outputs. And so that's a huge matrix multiply. So different people have come up with different tricks to try to reduce that. Schwenk was one of the first ones proposing an idea which is basically only predict the most frequent words and use an n-gram for the others. I don't really like this idea, but it gives some advantage. Then I and others worked on the idea of having hierarchical representations. So I think that's a much simpler and actually works well in practice idea. And let me actually explain it with so the idea is you define for each word a category, and maybe you can have subcategories and sub-subcategories. So you have a tree of categories, and your neural net, instead of predicting each of the words, just predicts the word categories. And if the number of word categories could be much smaller, potentially exponentially smaller or square root smaller than the number of words, this prediction is very cheap. Now, given the word category, you have another sort of part of the parameters of the model that tell you what is the probability for a subcategory and so on, until you get to predicting the word given the category and subcategory. So this is like a 3-level hierarchy. This one is 2 levels. But already with 2 levels, like in the picture here, so this is how you would implement it. You just have extra output units. You need to do something like square root of the amount of work you would otherwise need. And that's enough to bring it, to eliminate the bottleneck, basically, to bring the computation of the output part here to the same kind of range as the other layers. And so you can forget about the story after that. So that's a very simple thing. So you notice here you have lots of outputs, but you only need to look at the ones corresponding to the correct category for the word you observe. So when you train, it's very cheap. You only need to instantiate the outputs for the particular category of the word that you're looking at. Now, if you actually want to produce the probabilities for all the words, then it's expensive. But during training, it's fast. And then during tests, usually there are other solutions to speed things up. So there are also sampling methods that have been proposed to get around this issue of this output bottleneck. So I came up with some important sampling scheme several years ago. And then Colbert and his collaborators came up with a very simple idea. I mentioned that earlier today when I gave you this thing about sampling, corrupting your example into some negative example, and then making the energy of the observed one lower and the energy of the negative example higher, so long as the difference was above some threshold. That's exactly what they're doing. So it works really well. The only problem is that it doesn't give you probabilities as output. So if you don't care about probabilities, you only care about having some kind of ranking, then it's fine. Or if you only care about this model to find the embeddings of the world and of the words, then it's fine as well. There's also another trick which is based on important sampling that we've come up with recently in the context of autoencoders applied to bag of words. So the idea is, well, let's say my input is a very high dimensional vector, which is also very, very sparse. So most of the entries in my inputs are zeros. And what do I want to do? I want to train an autoencoder on this kind of data. The problem is when I'm going to reconstruct here, I'm going to have to compute the probabilities for each of those bits, and there are lots of them, even those that were 0. this is what the correct training criterion tells me I should do. Now, for going from the input to the hidden units, even though this is high dimensional, it's very cheap because I only need to look up the non-zeros. When I multiply a vector that is sparsed by a matrix, I can ignore the zeros. I don't need to do any computation for the zeros. But for the reconstruction, I don't have that luxury. I have this dense thing multiplied by a dense matrix to produce a dense output vector. So the trick we use is we say, okay, we're gonna only compute the loss for and its gradient for some of these, and by being smart about which ones we're choosing, we can actually reduce the computation time by a whole lot. It turns out that we can guess which ones here are gonna be non-zeros, and mostly it's gonna be those that were non-zeros here. I mean, it's basically autoencoding, so it's gonna predict high probabilities typically for those that were non-zero here and low probabilities for those that were zero. So we always reconstruct the non-zeros and then we randomly pick some other zeros as candidates on which we're going to compute the loss, and that speeds things up by a huge factor. So up to now, the models I've been talking about essentially learn about representations for individual words, and then they can, you know, if you use kind of convolutional architecture, you can get representations for fixed size sequences. But what about like variable size sequences, like a whole sentence? So one of really nice ideas to do that comes from actually the early 90s by a guy whose name is Jordan Pollack, and has been taken up by Leon Boutou and Richard Socher independently. So let's say we had these word embeddings. In other words, you associate to each word some kind of vectors, some point in a representation space. So how would I represent something like the country of my birth? Well, if Richard was giving the talk, he would say around Germany, and if it was me, I would say around France. And so the idea is that these different sentences, like the place where I was born, you might be able to actually place them semantically in the same space as words. Maybe you'll need the space to be a bit larger and have more richness, but why not put them in the same space? So that's the idea. So we'll just, you know, find an embedding for them as well in the same space. Okay, so how is this going to work? We're going to use a principle of compositionality. So we already know in principle how to assign an embedding to each word. And to assign an embedding to a sentence, what we're going to do is we're going to start from the meaning of the words and the representation of the words, and we're going to have some kind of rules to combine them. So we're going to take the representation of the representation of birth, and we're going to have some operator that takes these two things as input and outputs a representation for my birth. And we can do that for every subsequence and form a kind of graph. And we'll see how we can choose that graph that in the end gives us a fixed size representation for a whole sentence. So that's the basic idea, and you can do that using recursive neural net. So what is a recursive neural net? Basically, you replace these operators here by a little piece of neural net, which is reused everywhere with the same parameters. And so if someone could give you the right tree, you'd be done, right? You know how to do backprop and so on. So how are you going to find the tree? Well, there are different ways to do that, but sort of the basic idea, I think, was first proposed by Leon Boutou and actually implemented and made that work by Richard Socher, is this. You're going to try all possible pairs here. You're only going to try like neighboring words, and you're going to try to compose them. So, okay, first this is showing what we would like to get at the end is some kind of tree like this whose structure reflects the true sort of syntactic structure of the sentence. And what we'd like to do is find representations for these intermediate nodes. So, how are we going to do that? We're going to use the neural net at each node, as I said. And let's forget about the details. Okay, so the way we're going to parse is we're going to try all possible pairs, consecutive words. and we say which one gives me sort of the highest probability. Remember, autoencoders also give you a kind of probability. I mean, they give you a reconstruction error or some kind of score. So you can say sort of which pair does the neural net likes the most to put together. And let's say it's this pair. So we're going to say, okay, so we're going to forget about the other ones and just keep this one and replace these two nodes by this one. And now we have what we already had as candidates, things to be merged. And we also have extra candidates like this. So we again look at all the candidates and see, okay, merging this one is the next best thing we could do. And we do that, and so on. And greedily, you can build a tree like this. Now, you could do better than greedy. You can do a search using some search algorithms. And then once you've built the tree, you could use a criterion not very different from the one I mentioned before, which says, make the score of the correct things better and make the score of the correct thing make better and the score of sort of competing things to be worse. And this is also connected to things people do in structured output SVMs called max margin models. And you can actually train these things in this way. And the way Richard has trained them initially is using sort of supervised, sort of labeled data in which we know what the right parse tree is. But really what you want to do is let the model discover the right parses. Okay, I'm going to finish with the NLP part here. And you can apply this thing to images, blah, blah, blah. So you can parse images as well. And move to this. Okay. So one of the issues that I mentioned was important in training deep nets is underfitting. In other words, there's a difficult optimization problem when you actually train. And we've seen there's probably combinatorially many local minima, and probably many of them are poor. So I'm going to present some hypotheses that need to be tested to try to explain how humans might be able to get around that optimization problem to some extent. So first hypothesis, when the brain of a single biological agent learns, so like one person alone, it performs an approximate optimization with respect to some endogenous object. So we're just saying, brains are learning by optimizing something. Hypothesis, I think most people agree this is a reasonable hypothesis. Second hypothesis, that learning is by gradual improvements, which means it's a kind of local descent. So we're doing optimization and we're doing it by gradually, improving something. And if you put these two things together, you have to conclude that we'll get stuck in local minimum. Furthermore, based on all the work we've done on deep learning, both from a theoretical point of view and experimental point of view, with local minima and so on, another hypothesis is that higher level abstractions in brains are represented by deeper computations, more levels, or a longer sequence of operations. So that's also quite plausible, but of course it's something that needs more testing than the first two hypotheses. If that's true, then we would conclude that learning in single human learners is limited by these local minima issues. Fifth hypothesis, basically just slowly building to the things I've been saying, a single human learner is unlikely to discover high-level abstractions by chance because these are represented by a deep subnetwork in the brain. So what I'm saying is that some things that I've called high-level abstractions are hard to learn by pure gradient descent on some objective. And if that's the case, it's hypothesis, then humans must suffer from the same problem. Now, all of these hypotheses, remember, notice I've written single human learner, right? So I was talking about a single brain learning, looking at examples coming from nature. And now in the hypothesis number 6, I'm starting to talk about other humans coming into the picture. So in 2009, I had this paper called Curriculum Learning, where I talk about how by controlling the way examples are presented to a learner, we might make the optimization problem much easier. And I used the idea of continuation methods to sort of explain how this might happen. By gradually transforming the learning problem from an easy one to a gradually harder one, we can actually find much better local minima than we would be otherwise able to. And so the hypothesis 6 here is that a human brain can learn high-level abstractions if guided by the signals produced by other humans. And these signals would act as hints or indirect supervision, just like in supervised learning, for these high-level abstractions. So that's a pretty strong statement. And one question one may ask is, how would other humans guide training of young humans' brains? There's a lot of probably hardwired stuff in our brain about our social interactions. And things like pointing is something that comes sort of for free when you're born, that you pay attention to someone pointing. Other animals don't have that. So if your mother points to something, your eyes will look in the direction of the place that is pointed to. And it's not true of other animals in general. So we have these little behaviors that probably help us get started to learn language. And how would the pointing behavior and other similar social interactions help? Well, for example, a very simple thing you could imagine from a neural network perspective is that you have, say, two humans looking at the same scene, so they share the same input, and let's say they have both some kind of deep Boltzmann machine, and they also have some kind of linguistic units, and these are two-way units. So these are sitting in the middle of your language areas in your brain, and they are connected both to your motor units and to your speech center, your hearing, if you're not deaf. Otherwise, they're connected to your visual areas. And they allow you to receive and exchange linguistic information through exchange of verbal words and so on. And so what happens is when this guy outputs something, it becomes data for this Boltzmann machine, and this Boltzmann machine tries to predict what this guy is saying. And in particular, I think we pay more attention to what other people are saying than to other events in the world. And so there's like a stronger weight on the log likelihood for these guys than for most of these bits. And so we're trying to predict what other people are saying, and that what the effect of that is that it gives it forces these intermediate units to learn representations which are predictive of what the other persons are saying. And how does that help us? Well, in a sense, it's a way to transfer information from brain to brain. Like, we can't directly transfer synaptic strengths because there are just too many of them, but through this very small channel, very noisy and tiny channel, we're able to send a few crucial bits that give hints about high-level abstractions in the world around us and help other humans figure out what is going on. And that's exactly what I'm doing right now. So we can go with language. We can go even further. Not only we can share, we see a lion and I tell the lion, dangerous, but I can do more than that. I can tell you a story about lions. You have never seen a lion, and you can build a mental picture in your mind, and next time you see a lion, you might use that knowledge. So this is really powerful. So all these arguments is also about how this relates to making the optimization problem easier, and I won't have time to go into the detail of that, but basically the idea is if we show sort of very simple prototypical examples, like we're doing in a talk, like when you're explaining something to a child, it's actually much easier to learn. And even though it's not the big picture, it doesn't have all the subtleties, it helps to anchor the internal representations around which then sort of gradual descent becomes easier. And in particular, it can turn problems that may be intractable of unsupervised learning, in which you would like to discover the underlying factors of variation, and maybe it's really hard to do that. Maybe it's kind of combinatorially hard to discover these factors of variation, by one which is much easier, because I tell you sort of these intermediate answers, at least for a few examples, and that's enough to just give you the right push to turn something that was, you would be very unlikely to find by chance into something you can actually figure out by local gradient descent. Okay, so that's interesting, because what I'm saying is that if other humans already had the knowledge of good internal representations, of good explanations for the world around us, they could guide the training of other humans. But the next logical question is, where did all this knowledge come from in the first place, right? And so that's the idea of cultural evolution, and many researchers and scientists have been thinking about this for decades, starting with Dawkins with his Selfish Gene book in the 70s. And so the last hypothesis I want to propose is that language and meme recombination provide an efficient evolutionary operator. So the memes are basically ideas, things we can communicate, and basically are the pieces of knowledge that go from one brain to another brain and then can go to another brain and so on. And this allows a rapid search in the space of memes. So now we're working in the space of memes, not the space of genes. So it's applying the ideas of evolution to memes, to ideas, rather than to genes. And thinking of building better brains as a search problem, but at a level of representation which is not synaptic connections, that wouldn't work, but ideas, memes. And that's much easier. And that allows us to build better high-level internal representations of our world. Now, the crucial thing about thinking of this from an evolutionary perspective is that this is very different from a purely random search. So you could think, okay, so culture is about just the addition of knowledge, where we take many, many humans, and by chance one of them finds something good and it adds to the pool of knowledge. Now, that's sort of the common view, but I think the evolutionary idea is much more powerful, and because we can have these recombination of memes, if you come from computer science, you immediately think, oh, maybe there is a kind of divide and conquer phenomenon going on. In fact, people analyzing genetic algorithms have been thinking about this as well, and I think that's very important. It's again using another exponential to fight an exponential. Remember, in my first lecture, I said, oh, we have the curse of dimensionality. It's an exponential combinatorial problem. The only way we can fight that exponential is by introducing more exponentials. And we've talked about depth as one way. We've talked about distributed representations as another way. And here's another way, by recombining ideas. And I think culture does that. Anyway, all these are theories, of course. So when I presented longer versions of this talk, and some people asked me, okay, but where do new ideas emerge? Well, they emerge at different scales. They emerge at the scale of seconds in your brain when you're doing inference. When you're trying to, what is inference? It's trying to find an explanation for what you're currently seeing. And sometimes you come up with a novel explanation. Inference has a bit of a stochastic nature, and you're faced with new things. And these new explanations may, bring you to better models of the world through learning. Learning is going on at a slower scale, maybe minutes and hours and days. And it's basically a local descent. And it's pretty much like our current deep learning algorithm, and maybe we can do better, I hope we can. But it's some kind of local descent. And then at a much slower time scale, I guess it's going faster now with the internet, is cultural evolution. And that's a kind of global optimization. It's very different from that kind of optimization. And it's based on recombination of ideas from other humans. And so new ideas are coming, into life through all of these three processes together. Okay, so I'm done. You can find pointers to, so this was actually for the NLP thing. You can find lots of pointers on my web pages. In particular, There is the deep learning tutorial for NLP I mentioned. There's the deep learning tutorial I gave at ICML. And of course, you can find the slides for this tutorial for these lectures on my webpage as well. I've put in pointers to software. Blop. I'm done.